Here is the word momentum in really big letters, which is the subject of this video. Momentum can be thought of as mass in motion, which is fitting because the formula for momentum is mass times velocity, which can also be written as P equals m times v. So, two objects with the same velocity but different masses have different momentums. Take these rockets. The red one has mass 10 kilograms, while the green one has mass 5 kilograms. So even though they're traveling at the same speed, they have different momentums. The same logic applies to objects with the same masses but different velocities. In this video, we're going to look at closed systems. A closed system is a system that has masses moving at velocities with no external forces acting on them. Another way to think about it is that the vector sum of external forces equals 0. Now, momentum is also a vector. It has both magnitude and direction, like velocity and acceleration. What this means is that an object with mass m and velocity v does not have the same momentum as an object with mass m and velocity negative v. So m times v is not the same as negative m times v. Next up, impulse, a change in momentum. We can actually relate force, momentum, and impulse using the equation force equals mass times acceleration, or F equals ma. Since acceleration equals change in velocity over change in time, we can rewrite this as force equals mass times the change in velocity over the change in time. We can rewrite this again as force equals the change in mass times velocity over the change in time. Notice that the right-hand side is now the change in momentum over the change in time. Finally, multiply both sides by the change in time to get that force times the change in time is equal to the change in momentum, or impulse. So, putting everything together, impulse is equal to the force applied over time. So in order to change an object's momentum, you have to apply a force over a unit of time. Remember, impulse is the change in momentum and is equal to force times the change in time. We can divide both sides of that equation by time to obtain force equals impulse over time. To understand this intuitively, imagine a car speeding down an empty road. When you hit the brakes, a constant force is applied to the car. The value of the force is the change in momentum of the car, or the impulse of the car, divided by the time it takes to stop. So if the car were to brake harder, you'd see this translate into the car stopping sooner. Next up, we're going to talk about collisions, and more specifically, the difference between elastic and inelastic collisions. So first up is elastic collisions. In an elastic collision, both momentum and kinetic energy are conserved. As you can see with this red ball, no kinetic energy is lost when it hits the bottom and comes back up. Each time it bounces against the bottom of the screen, it comes back to the exact same height, because all of the kinetic energy it has going into the bounce is the same amount as it has coming out of it. Now consider this yellow ball, which is an inelastic collision. Momentum is also conserved, but kinetic energy is not. Some of it is lost, it loses heat energy, sound energy, so the ball bounces back to lower and lower heights. Remember, the difference between elastic and inelastic collisions is whether or not kinetic energy is conserved. In both scenarios, momentum is conserved. So this brings us to our last topic, the conservation of momentum, which we've sort of been leading up to with our discussion of collisions. So what exactly do we mean by conservation of momentum? Formally, for a collision occurring between two objects in an isolated system, the total momentum of those objects before the collision is the same as the momentum after. So if one object loses momentum, the other object has to gain the same amount of momentum. Let's go through an example. We have this explosive collision. It's an elastic collision, so both momentum and kinetic energy are conserved. The particle coming from the bottom left, it has a mass of 1 gram, and obviously particles weigh less than 1 gram, but we're going to pretend that this particle weighs exactly 1 gram, and it has a velocity of 10 meters per second. The particle coming from the upper right also has a mass of 1 gram and a velocity of negative 10 meters per second. What is the velocity of both after they collide? We need two equations for our two unknowns. Fortunately, we have two equations. The fact that momentum is conserved gives us the first one, and the fact that kinetic energy is conserved gives us the second. So to begin, let's find the initial momentum and the initial kinetic energy. The initial momentum is m1v1 plus m2v2 equals 1 times 10 plus 1 times negative 10 equals 0. The initial kinetic energy is 1 half m1v1 squared plus 1 half m2v2 squared, which equals 1 half times 1 times 10 squared plus 1 half times 1 times negative 10 squared, which equals 100. The final momentum has to be 0, and the final kinetic energy has to be 100 because it's an elastic collision. So, final momentum can be written as 1 times v1 prime plus 1 times v2 prime equals 0, and final kinetic energy as 1 half times 1 times v1 prime squared plus 1 half times 1 times v2 prime squared equals 100. If we rearrange the first equation, we'll get v1 prime equals negative v2 prime. Let's substitute this into the equation for kinetic energy. So now we'll have 1 half times 1 times negative v2 prime squared plus 1 half times 1 times v2 prime squared equals 100, which gives us v2 prime squared equals 100. Take the square root of both sides, and we get v2 prime equals 10. If we substitute this into the first equation, we'll get that v1 prime equals negative 10. This result, the objects switching velocities, actually happens every time we have two objects of equal mass and equal and opposite velocity colliding into each other. They'll take on each other's velocities and start moving at the exact same speed in the opposite direction. What's even more interesting is that when two objects of equal and opposite momentum collide into each other, they actually take on each other's momentum. So two objects with different masses and velocities, but if they have the same momentum with opposite signs, once they collide, their momentums will switch. And that's our video. Thanks for watching. I hope you learned something, and I hope you were at least mildly entertained.